So welcome everybody and thank you for coming. So today's speaker is Robert Whitney from a lab which also depends on two institutions like our institute, the University of Grenoble and CNRS. So I would like to say a few words about him. He got his PhD in 1999 in Birmingham under the supervision of Lerner, and then he had a few postdoc positions, all of them in well-known institutions like Weizmann in Israel, Oxford University, Geneva, University of Geneva in Switzerland. And after that, he got a permanent position in Grenoble as part of the research staff in this lab. So he's obviously his main field of research is quantum transport and mesoscopic systems, but these days also he got interested in random walks in classical systems like ecology. Tigers, you mentioned? Tigers?
I don't know anything about it yet, but I'm trying to learn about it at the moment.
About the tigers or about the random walks?
A little bit about the random walks and zero about the tigers.
Okay, please.
Okay. So, thank you very much. So I'm going to talk about thermoelectric effects today. And my work on using thermoelectric effects for refrigeration in systems where quantum mechanics is very important. So typically nanoscale systems which are already at very low temperatures, and one question is, can you go to even lower temperatures? So the outline of my talk, the first thing I'm going to talk about, and I'll take maybe quite a while to talk about that, is the general interest in thermoelectricity. And particularly I'll say some things about why engineers are interested in thermoelectricity, which is not at all my area of expertise, so I hope I won't say anything too stupid. But I'm interested in pure physics, and I think there's interesting physical problems here. But of course I'll start off motivating it by saying it's really important for the future of humanity in terms of practical applications. And particularly from my point of view, what's interesting is that a good refrigerator is rarely a linear system. It's typically highly out of equilibrium, and so it should have very rich non-equilibrium physics. Then that will be the introduction. Then the things I'll talk about in my work will be in two parts. One will be talking about a particular quantum system where I think we can do the theory and understand really more or less what's happening and see some quite rich nonlinear effects. And then the second part will be to ask about more general quantum systems and ask what are the equivalents, like in traditional thermodynamics, there's things like Carnot efficiency, and there are bounds on how good a heat engine or refrigerator can be. So now in this quantum system, I want to ask what are the similar bounds on an arbitrary quantum system. Okay, so I guess this second part I won't have much time, so it'll go a bit quickly. Let's start with why people in the street should care about thermoelectric effects. Well, most of our life is dominated by these two things. Either you have heat, which you burn something and you want to make electricity, or you have electricity and you want to cool things down. Okay, and these two processes are extremely important in life, and to do them efficiently is incredibly important. And there's a third thing which we do very little of now, but people want to do more and more, which is to recover waste heat. So this is a picture from the US Department of Energy, which says, I don't know how well you can read it, but if you take your car and 100% of the fuel that's burnt in the car, only 12% goes to actually making the car go along the road. 60-something, around about 60% is lost in friction and other heating effects. So friction means the motor's heating up, actually a big proportion of this is the heating of the exhaust gases, so the exhaust pipe gets hot. So more than half of your petrol is just going to heat things up. So the idea would be, well, can we capture this heat in some way and turn it back into electricity, which we could use to make the car run along. So how do thermoelectric devices fit in here? Well, here you see we have classical pumps. We have some fluid going around that's connected to some turbines and so on. And in both cases of a normal kitchen refrigerator or a power station, there's classical fluids. But nature has given us something else, which is a thermoelectric effect, where just by, so this is some real thermoelectric devices, and by heating one side of this device, you can generate a current between these 2 points. Okay, I'll explain in a moment how that works. Or similarly, if you supply a current, you can pump heat between the 2 plates. Okay, so you can use it in either as a refrigerator or as a heat source, as a power source. And the hope is that in the future, these sorts of things will be extremely efficient and will solve most of the world's energy problems. Okay, the problem today is that most of these devices don't have very good efficiency, which is why the refrigerator in your kitchen still uses a pump rather than a thermoelectric device, because a pump has a better efficiency than a thermoelectric device at the moment. And if you look at most of today's thermoelectrics like this, the sorts of things you can find if you look on eBay or on some website is this, which is a thing to cool down, so the photos may be not very good. You put your can of Coke or other fizzy drink in here, you connect this to your USB port of your computer, and it's supposed to cool it down. Okay, so this is quite a big step from solving the world's energy problems. And apparently, I read a review of one of these things, and that some guy on the internet had tested it, and he claimed that the cold plate inside this only managed to cool down to about 7 degrees. So that means that depending how well insulated it is, you're never going to get your can of Coke really cold. So it's that, for example, is not cold enough to keep, if you wanted to keep your meat fresh or vegetables fresh for a few days, that's not cold enough. Okay, so now I'm being a little bit rude because that's not the only use of thermoelectrics today. Another use is in space probes. So the rover that's running around on Mars at the moment has I think it's a nuclear heat source, so some uranium or whatever, that generates heat, and all of its systems are powered by a thermoelectric device which generates, I think, 100 watts or something like that. Okay, so so how do all of these thermoelectric devices work? This is what we're interested in as physicists. And what's nice is that they work by having different properties for electrons and holes. So we have, for example, here a hot region and here a cold region. Let's say it's at 0 temperature. So the hot region, there are lots of electrons above the Fermi surface, and there are lots of vacancies, lots of holes below the Fermi surface. Okay, and you want to couple it through a system to something at low temperature where there's more or less no electrons above the Fermi surface and no holes below the Fermi surface. Now, if you just coupled it through a normal metal, then the electrons would flow, the holes would flow, there would be a heat flow, but no electrical current would flow. However, if you arrange the system that it's coupled through something with a gap in its density of states, so it could be a semiconductor, for example, and you arrange that the gap is asymmetric with respect to the Fermi level of the two systems, then the electrons can flow through, but the holes can't flow through, they get reflected. Okay? The alternative way to think about it, if you don't like thinking about holes, is that there are lots of electrons here that would like to go into the empty states here, but they can't because there's no states for them to flow through. So the result is that by heating this side, you get an electrical current. Okay? Now, there's a similar argument, a bit more complicated, that says that if you manage to pass an electrical current, so you put a bias on this side and push an electrical current, it will make heat flow. So you can use it either for refrigeration or to generate power from a heat gradient that you already have. Okay, so then typically what one does is has two different systems with one would have the gap in its sensitive states. This would be an N-type semiconductor where the gap is for the holes, and the other one would be a P-type where the gap is for the electrons. And then, as a result, if you want to cool down this point in the middle between two semiconductors, you pass a current, and in this one, the heat flows in the same direction as the current, and in this one, the heat flows in the opposite direction to the current, and as a result, heat is always flowing away from this point, so it will cool down. Okay, and then the realistic systems, like the one I showed on the previous transparency, typically have many of these in series. So you have one P-type, one N-type, one P-type, one N-type. So then when the current passes like this, the heat always flows in the same direction. Any questions? I should have said that at the beginning. Please interrupt me if you...
This is a normal PN junction.
Absolutely, yeah.
And everything you say is that when there is current flow, it cools down.
Yeah. So I think probably if you take an arbitrary PN junction, so that I'll mention this a bit later on, the big problem is that there are also lots of phonons in these systems. So if you take an arbitrary PN junction, if you cool this guy down a little bit, all of the phonons which are hot will flow into the middle and compensate for the cooling. So you maybe won't see very much cooling. The materials that they typically take to do this are very carefully chosen based on experience and things that people don't really understand, such that, and probably a lot of it has to do with the fact they're rather poor phonon conductors, so they're rather poor heat conductors, and then when you cool this guy down, there's an appreciable effect. So I'm not sure if you take an arbitrary PN junction that you'll see anything very much.
That's what I was surprised at.
Yeah. I think there's a subtlety. I mean, already most of these systems aren't very good, and even the best ones in the world aren't that good. And so I guess if you just take an arbitrary one off the shelf, it will be really almost negligible effect, just because heat will very quickly flow into the middle. So now we come to how you measure the quality of these systems. And this is a good point because it brings me on from the question. So the quality of these systems is defined in terms of what's called ZT for historic reasons. And it's got the Peltier effect, which is the thing that drives the fact that you have a you have a current flow due to the heat flow upstairs, so that's good. You need the Peltier effect to generate this sort of thermoelectric effect. But you notice underneath you have the thermal conductivity. So if you have a high thermal conductivity, it's bad news for these devices. So particularly the phonon part you really want to get rid of. Okay. Now the best current semiconductors typically have a ZT of order 2 at best. And they claim that if you want to replace the fridge in your kitchen, probably a ZT around about 3, it would start being interesting to be more efficient with these thermoelectric things than with the pumps that you have. Now, there are various theory proposals from the last few years which are proposing a ZT up to 10 or even more. Now, some of these proposals you have to be a bit careful about because they haven't always taken into account the phonon physics very carefully, so they've tended to neglect this term, so it sort of overestimates. But there's still a lot of interesting things, and many of them going on thinking about connecting using molecules rather than bulk semiconductors. Okay, and so I have a list of quite a lot of papers on this subject in the last few years. But an important point from what I'm going to talk about here is that this ZT is an estimate based on linear response coefficients. So it's the linear response conductance here, it's the linear response electrical conductance upstairs, and the linear response Peltier coefficient. And the point about a refrigerator is that if it's any good, it will very rarely be in the linear response regime, because you turn it on, you start with the temperature of the thing you're trying to cool down at room temperature, you turn it on, the temperature goes down and down and down. You want a device that manages to reduce the temperature a lot, and once it's reduced the temperature a lot, you have such a big difference in temperature that you're in a very non-equilibrium situation. Okay, so once you have a device that has a good thermoelectric response, when you use it as a refrigerator, it will always be in the nonlinear regime, and this quantity may no longer be a sign of how good it really is. Okay, and I'll give an example of cases where this ZT figure is a very bad measure of how good a refrigerator system is. Okay, so where are we now? Okay, so now I just want to mention one more application which is much more in physics than many of the things, which is to think about refrigerating nanostructures. Okay, so at the moment in a good cryostat you can refrigerate a nanostructure down to about 40 millikelvin. Okay, and there are many experimental systems where we would like to study them at even lower temperatures for all sorts of reasons, looking for phase transitions or quantum phase transitions or all this sort of stuff. And the problem in experimentally to go to lower temperatures is that typically the cryostat cools the phonons, and then the phonons are cold, and so they couple to the electrons and they cool down the electrons. But the problem is that when you go below about 1 Kelvin, the coupling between the phonons and the electrons becomes very weak. So even though you may be cooling down the phonons very well, the coupling between the phonons and the electrons is so weak that the electrons have a tendency to remain hot. Remain hot means remaining perhaps at 1 Kelvin or half a Kelvin, something like that. Now the advantage of thermoelectric effects is that they directly cool the electrons. So if you're interested in the physics of electrons at low temperatures, then once you go below about a Kelvin, it may be much smarter to then have a thermoelectric refrigerator inside your cryostat, which can take the electrons down to a much lower temperature. Okay, and it's not clear at the moment what the limit on this would be. It's very early days in this sort of research. So you might hope to get to 1 millikelvin. I don't know if that's reasonable. But what I can say is that there have been some experiments. Even the first one was done in '96, and quite a bit has been done recently in Grenoble, so I'll advertise that, where they take a system made of superconductors and metals, and I won't go into the details of this, but approximately the superconductors, they have a gap in their spectrum, the superconducting gap, and this works more or less like a p-n junction, but now the energy scales are at the level of a Kelvin rather than the level of room temperature. So, so this device has been observed in the experiments to cool down from around about 300 millikelvin, reducing the temperature by a factor of 3. So as a first step in this direction, it looks promising. And what's very nice now about in this business is that people are starting to have good experimental probes of temperature, which maybe didn't exist so much 10 years ago. So by various techniques, which unfortunately I won't have time to discuss, people can actually now measure the temperature of some little micro or micron size metallic island in the middle of a cryostat. And that means that as a theorist, we're not talking in thin air. We can actually calculate something and compare, say it should be at this temperature, and the experimentalists can actually come and look and see what the temperature of their device really is. So the question is, if you want to cool down a little bit of metal of size of 1 micron in your system, can we maybe not use thermoelectric effects to do that? Okay, so I guess that's the end of the general introduction. Now we get some more technical stuff, which is the standard textbook theory of refrigeration. Okay, so the standard textbook theory of refrigeration is based on linear arguments, so linear response theory. So we say that the heat flow out of the thing we're trying to cool down has a Peltier effect, which is, so this is the heat flow into the thing we're trying to cool down. So it has a Peltier effect with a minus sign, so that's sucking heat out of the thing we're trying to cool down. But in competition with that, there are two positive terms here. The first one is just the thermal conductivity. Once the thing we're cooling down is colder than its environment, there'll just be heat flowing due to thermal conductivity. Phonons and electrons will all contribute to that. And the other term is Joule heating, which says if I pass a big current through the system to try and cool it down, so this guy looks like it will be good if we want to cool it down the most we can, we suck out the maximum amount of heat by making the current as big as possible. But it's competing with the fact that when we pass a big current through a resistance, it heats up the resistance. So there's this term which heats up the resistance. And so there's a competition between these two with a quadratic form. You see that this is I squared and this is I. So it's not hard to guess more or less what the solution of this equation is. So in this region, the heat current is, I guess, in this notation, it's negative, which means you're cooling down the system. And down here, the heat current is positive, which means you're heating up the system. And the two regions are separated by a parabola, which is basically this guy. So if I plot temperature on the vertical axis, so I want to cool the system down, and I plot the current that I apply. If I apply an arbitrary current here, it starts at room temperature, which is 1 on my axis, and cools down to this point and then stops there. If for some reason it was colder than that, it would heat up to this point and stop there. Okay, so then it's clear to see this is a parabola, so the optimum current to apply, which is from the competition between these two terms, brings you down to here, and so this is the minimum temperature of the system. So you complete the square, that's nice and easy to find this minimum temperature, and it is given by this figure of merit, this ZT, which I talked about a moment ago, with this strange combination of the linear response coefficients. Okay, so that looks good, except you see that this is a linear argument, and for the particular parameters that I chose for this curve, you see the temperature, when you've cooled down to the steady state temperature, the temperature you've arrived at is maybe 1/3 of the environment temperature. So this is a big difference in temperature, in which case you'd say, well, this doesn't look like a linear response type problem. This difference in temperature is so big that I can't neglect higher order contributions that go like the difference squared and the difference cubed and so on. So I really need to do something better than that. I need to look at nonlinear effects.
So Rob, why the 1/2 in the Joule heating term?
That's a good question, and I don't have a particularly good answer. In most systems, when you heat up the resistance in the middle, half the heat goes to the cold side and half the heat goes to the hot side. Okay. So if you're interested in the heat flow on the cold side, it feels half the Joule heat. So that's the factor of a half. Now, when is it exactly a factor of a half and when is it some other factor? In the textbooks, it's always a factor of a half, and in many systems, half is the right number, but it's pretty unclear, I think. You can find plenty of systems where it's not a half.
It's kind of flow partition, right?
Yeah, so there's some...
This can be done in many ways.
Yeah, absolutely. So you need that... I mean, conservation of energy tells you that without the factor, the total energy heat flowing out of the resistance should be this without the factor of a half. And then somehow it will be divided between the two reservoirs. So, okay. So I guess that's now the introduction of the end of the introduction, and I am ready to start thinking about nonlinear effects. So I decided to take a very simple quantum system, which has a well-known thermoelectric response, which is a point contact, and try and do a fully nonlinear, non-equilibrium theory for it, and look at how the results compared with the one that I just plotted. So this is a pretty tough problem, and there's the list of literature. So the important things here are, so there's old literature on how to do the linear response with the Landau-Bettius scattering theory. Then ways of including nonlinear effects, particularly interaction effects, is more recent. And in the last, basically in the last year, there have been a whole bunch of us, including people who are sitting in the front row, on looking at nonlinear effects in these sorts of thermoelectric systems. And I apologize, I didn't update the reference here to physical review letters, I should say. This nonlinear scattering theory is sort of well known and has been applied, but I should just mention, if there's anyone in the audience who knows this scattering theory, there's another competing scattering theory which I just want to draw attention that it's not this one if you know about that one. If you don't worry about it. Okay, what does the scattering theory look like? Well, I guess this slide is not very helpful in the sense that if you already know how to do scattering theory, you know all this stuff. The idea is that if you have a current generated by a difference in the distribution of particles on the left and the right. So these are Fermi functions on the left and the right of the system. And the crucial point is that in the middle there's this scattering matrix, or this transmission matrix, which is made up of scattering matrix, which tells you basically if a particle is coming from the left into your quantum system, what is its probability to be reflected and what is its probability to be transmitted. Okay? And then once you have that information, you've basically completely characterized the system, and you can get all the currents that you want based on whatever distribution of temperatures and heats you have in the system. Okay, now the problem with the nonlinear response is that the probability of particles being transmitted or reflected inside the system changes the distribution of particles in the system. And because the particles interact with each other, they feel each other. So if there's more particles, if they pile up at one place in the system, then they will repel other particles from that place in the system. So in the simplest approximation, which is a Hartree style approximation, you can treat all of this with a self-consistency loop where you calculate the potential distribution in the system due to where the electrons have gone in the system, which is given by the scattering matrix. But then you need to do this self-consistently because the scattering matrix itself is a function of the potential inside the system. I don't know if it's worth drawing a picture of this. So if I have some nanostructure that I've made, something like this, and it happens that particles are coming in here, then what if lots of negative electrons for some reason go to this region, then the scattering matrix, the other electrons coming here will be repelled from this region and will do something else. And so one needs to self-consistently calculate where the electrons go with the potential inside the system. Now in general this is an incredibly hard problem, probably in many cases insoluble. But in a few cases, you can make some progress making some simple model and some simple assumptions about this problem. Okay, so...
I think there's a missing sum over J, right?
Oh, probably, yes, that's embarrassing. Yeah, okay, yes, you're right. There should be a sum over, so there should be a sum over all incoming leads. So this is the outgoing, and you should be summing up over all of the incoming particles. Yeah, absolutely. Okay, so now this is just a point. I made the point earlier about getting rid of phonons, and so I just want to advertise some nice experimental work that's also being done in Grenoble on minimizing the effect of phonons. So normally when you build these sorts of nanostructures, they're just on a thick substrate, which means that all of the phonons in the substrate can come into the nanostructure and escape again, causing very rapid thermalization. But here they can now make systems where the platform on which you do your experiment is suspended by these 4 wires, so it's suspended above the surface, and then no phonons can go between the two. The only thing you can get is phonons traveling along these arms. It's the only way for heat to get back into the system. So the idea would be to make an electrical circuit here with some thermoelectric effects, thermoelectric systems here and here, to try and cool down this, the electrons inside this island. Okay, so so this is a sketch of what I want to do. So I want to pass a current through some point contacts. Some point contacts, as I'll show in a moment, have a nice thermoelectric response. To cool down this island that is suspended above the surface like that. And then I need to take into account the heat currents that I suck out of these two systems, and then eventually the phonon and photon contributions of when this is cold and this is hot, then heat will be radiated by photons from here to there, and also by phonons moving along these arms into the system. Okay, and I'll stick with this sort of problem, but probably in the future a more realistic thing would be to have many of these guys in series to cool down maybe a larger island. Okay, so let me first, so now let me zoom in on what's happening in one of these point contacts. So here I have a region where the electrons go through a very narrow constriction, and in this case I'm thinking that it's probably defined by putting metallic gates on top which repel the electrons, so they end up just in this very narrow channel. And if this channel is narrow enough, then the potential landscape can look something like this. Okay, so in the middle the electrons are trapped. They almost don't have enough kinetic energy to go through. So the result is that on the side that I'm trying to cool down, the temperature is low. And on the side that is my environment, the temperature is high. So you see the electrons, there are many electrons above the Fermi surface and many holes below the Fermi surface. But now if I bias the system, so I put a positive bias on this side, so it pushes the chemical potential for the electrons down, then I see that what happens is that electrons in the island can escape, but they're not replaced by anything because all of the electrons of order temperature above the Fermi surface are too low to get over the barrier. Okay, so this is going to cool down the island because these electrons eventually will run around and will eventually escape. The holes will run around and will eventually escape on the other side. If I construct the system such that it has the opposite thermoelectric effect on the two sides. So, for example, if this one the charge carriers are electrons and on the other one the charge carriers are holes. Okay, so this I call, following the literature, pinch-off, meaning that the chemical potential of the island is just right that the electrons can't quite escape over this barrier. If the potential was lower, then immediately you'd get a lot of electrons flowing, so you'd get a big current flowing. Okay? If the potential was higher, then nothing would happen, or very little would happen. And I'm going to claim that with all of the interaction effects, you can still always use these gates to tune such that the level, that the height of the barrier is just where you want it to be for this effect. Okay. Now, so what's the result of all of these calculations? So this is the textbook theory. So I now put in all of the machinery that I won't go through. And what's nice about this model is that it may not be the best model for it may not be the best thermoelectric device, but you can get all of the results analytically without doing any simulation. You just plug in the formulas and you get ugly answers like this, where this is a dilogarithm function. So if this was a normal logarithm, I'd say, okay, there you are, that's the answer, you all see what it looks like. But because none of us remember or none of us know what a dilogarithm function looks like, I certainly didn't know what it looked like before I found it here, I get Mathematica to plot this function. And what does it look like? Well, instead of looking like this parabola, it now looks approximately like a parabola, but in the opposite direction. And this is very weird, because this is what in mathematics is called what's called a fold-catastrophe in mathematics. So if I start at room temperature and I cool the system down using a given driving current, it gets to here. Okay? And this is the steady state. However, if by some magic, for the same driving current, I managed to start with it in this region, it would cool all the way down to this steady state. Okay? And these two, so we have, in this part of the phase diagram, we have two stable states and one unstable state. And then at this point, the two annihilate, and you're left with just a single stable state once I have currents that are bigger than that. Okay? So, so this is fairly standard in nonlinear systems, I think, but it's very nice to see it in a problem like this. And what it tells you physically is that you drive this system at relatively low currents and you see a relatively weak response. But if you manage to drive it at high enough currents that you can get down to this steady state, then suddenly the response of the system is much more interesting. And if you can manage then to adjust the current to drop the current to go down here, in principle, you can cool all the way down to absolute zero. In principle, these two, the stable and the unstable steady state, meet at a point at zero temperature.
Can I do two questions? One, I don't know if it is trivial. Is there any role of electron-hole recombination in all this process?
No. So that's quite an important issue. The fact that at the scale of the point contact where all of the interesting physics is happening, energy is conserved so that the electrons flow through without changing their energy. And if there are relaxation effects inside the system, that could change everything. So if you have electron-hole recombination, or that could easily change everything.
So, but is that an assumption, or
as a theorist, that's an assumption. Experimentally, I think these length scales are normally extremely long compared with. So this is one of the interesting things about low temperatures. At very low temperatures, you have extremely long relaxation and decoherence times. So even the length scale for electrons just to scatter off each other becomes, I'm trying to think, it's typically can be as much as fractions of a millimeter when these sorts of structures are on a nanometer scale. Okay, so. Yeah.
Typically, one expects to observe nonlinear effects when you increase something, when you increase the current, when you increase, then there is, of course, other effects. Here, the most of the effect is at very low intensity or just on that part. Why the linear theory fails just at the point where one might expect to be more successful?
So the linear theory works well here. Okay, the scales aren't the same on the two plots. So this is the sort of linear theory, and in fact, the real curve comes down like this, like the linear theory, but then does that.
But then this is the part of very low intensities.
Right.
So this is the one that is new.
Okay.
New branch.
Okay, so I tell you, that's a nice question because there's something hidden here, which I was thinking probably to leave hidden, but I'm very happy that you asked about it. What's hidden here is the fact that here I'm plotting the current. I'm not plotting the bias. And the reality is, if I take this plot, and I managed to cool this guy down to very low temperatures. Even if there's a very, very large bias, basically there are almost no particles to escape. So the current, when you take the temperature to zero, the current vanishes, even though you have a very, very large bias. And here, that's more or less exactly what's happening here. This stable, steady state is in fact infinite bias. And then the amount of current that you can get at infinite bias is decays with temperature. So it looks like, so I think that's answered the question, that it's not at all an equilibrium state here, even though the current is small. Yes, thank you for that question.
Coming back down to time scales, I mean, you have coexistence of two stable states. So in some sense, both of them are, or one of them is metastable. Any idea of the time scale of relaxation from one to the other?
So because they are at very different biases, if you experimentally are applying a given bias, then I guess there's no chance of relaxation from one to the other. If, on the other hand, you have a situation where you're applying a steady current, then probably there is, and I haven't thought about it carefully. And I think the problem is it will depend on the physics of your current source, I suspect. I haven't thought about it. But,
because of the past history.
So,
no, the past history is which branch you go. But what I'm asking is, what is the typical time scale to relax spontaneously from one branch to the other?
It will depend on the intensity of the shock noise and the intensity of these kind of things.
I guess, for example, if you make a model of the circuit that this system is embedded in that generates the voltages and the currents, and that circuit has some capacitance and some inductance, I suspect there'll be some sort of RC time, something like that will enter into it. Because I think if I imagine that I apply a fixed current, then the time scale for hopping between the two will be infinite. So I think I need some sort of more sophisticated model to get that. But it's a very good question, actually. I haven't thought carefully about that. Yeah. So how are we doing for time? So we're going. So that's the main point. Is that here when I cooled down, I reached a minimum in temperature, and here it looks like I can cool all the way down to absolute zero. And this is with a point contact which is known to not be a particularly good thermoelectric device. It has this ZT of 1.5, so very typically, and already it has these very strong nonlinear effects. Okay, so now the question is, I guess that's the next, what's the next transparency? Yes, about parasitic effects. So can we really cool down to absolute zero? Well, of course the answer is no. And the reason is because I've completely neglected the phonons and the photons and all of that sort of stuff up until now. So I think I probably will skip over the details of modelling phonons and photons, but let's say that we have like a Stefan Boltzmann law, that you have a hot environment radiating heat into the cold system you're trying to cool down, and so you can model it with some suitable radiation, and you put in some suitable numbers from the experiments, and then you plot what the results are. So the black curve was the steady state without any phonons or photon physics, and if I take typical experimental parameters, then I'm somewhere in this region of curves. So what happens is, as I turn on the phonons and the photons, instead of cooling all the way down to 0 temperature, I cool down to this point, and then I don't go any further. Okay, so the steady state is the blue curve joining on to the black curve. If I increase so the first thing is I don't get to absolute 0. But then the second thing is if I increase the coupling to the environment, the catastrophe stays there for a while, but then it becomes a cusp. Okay, so from now, when I have strong coupling to the environment, then the minimum temperature I can get to is at a cusp of the response as a function of current. So it's instead of there being a discontinuity in the temperature as a function of current, I have a discontinuity in the derivative. Okay, and so now we can do similar things for a heat engine. So there I was talking about refrigeration, so using electricity to make a temperature difference. If I have a temperature difference, I can look at how much electricity I can generate, or how efficiently I can generate electricity. And the only thing I want to show is that, so the straight line is the linear response prediction. And you see that for a given phonon coupling, the solid line, say the black line, is below the linear response. So what this tells you is that the point contact is a better refrigerator than linear response would tell you, but it's a worse heat engine than linear response would tell you, particularly when the temperature differences are very large. So when the temperature differences are very small, linear response works very well. But as soon as the temperatures get very large, it moves away from linear response, and it always gets worse than linear response. Okay, so that's the main message. I think I'll skip over that. So now, how much time? Did we start on time? I guess we started more or less on time. So, okay, so we have 10 minutes. So now I'll just advertise some new results I have on sort of trying to understand what are the equivalent of thermodynamic limits for one of these quantum systems. Okay, so so now I'm thinking about an arbitrary quantum system. Could be quite complicated with many reservoirs, perhaps some superconducting reservoirs, all sorts of scattering going on in the middle. And what is fairly easy to see is that, so if you like, the zeroth law of thermodynamics, or part of the zeroth law of thermodynamics, is about the definition of equilibrium. And it's quite easy to see that indeed this system has the right equilibrium properties to fit with the zeroth law. The first law of thermodynamics is about energy conservation. It tells you that if heat generates work or work generates heat, the sum of heat and work should be conserved. So that's natural in these sorts of scattering theories because the scattering theory conserves energy. So we have the first law of thermodynamics almost for free. However, the second law of thermodynamics is much more mysterious. Okay? The second law of thermodynamics tells you about entropy change, which is all about dissipation. And in these scattering theories, one typically doesn't include dissipation. What one says is, well, somewhere in the reservoirs there's some equilibration process that turns all of my non-equilibrium distributions into equilibrium ones and dissipates all of the work that's been done, all of the weird things that have happened, and that's not really included. That mechanism's not included in the theory, it's just included in a boundary condition. So there's no microscopic model. And that would at least make me suspect that if you ask questions about entropy production, that wouldn't be good enough. This sort of very naive model, I expected you'd have to include some of the physics of how energy and information is relaxed in the reservoirs before you get the right second law. But it actually turns out that no, just treating the reservoir as some black box where dissipation occurs is enough when you do this nonlinear scattering theory carefully to see that the entropy of the total system, you know, all of the reservoirs summed up plus the system, always increases. Okay, and this was noted in a paper by a group in Marseille from earlier last year, and not knowing about their work, I was working on the same thing and managed to include also superconducting. If you have a superconducting reservoir, it still holds. If you have various dephasing and relaxation properties inside the nanostructure, you still always get the second law of thermodynamics out. And it all comes from, well, okay, I'll say that in a minute. And then the final thing that you have in addition to the classical laws of thermodynamics is that there's a quantum bound on the amount of heat that can be extracted from any reservoir. So it doesn't matter what system you put here, how much power you supply to it, there's a quantum bound on how much heat can be extracted from this reservoir, which has a very simple interpretation. It basically means if there's an electron here above the Fermi surface, it comes to this point, and either it is extracted or it's not extracted. But you can't extract more heat than if you pull every electron that's above the Fermi surface out of this guy. And as there's a finite, or they arrive at a finite rate, you can't extract heat faster than that rate. And that was noted for systems without thermoelectricity by Pendry quite a long time ago. And it gives you a quantum bound which is dependent on the number of modes in the lead. So it goes like 1 over the wavelength of the particles here. So if the wavelength is strictly 0, then you go back to classical thermodynamics with only the thermodynamic laws. But as soon as you put a finite wavelength, then there's a limit also on the amount of heat you can extract. So I'll come back to this in a moment. Let me just say a couple of things about the second law. So the second law, what have we done? We've taken a concept of thermal equilibrium in the reservoirs, plus a Schrödinger equation for the system, which is coupling the reservoirs. Okay, so it's a Schrödinger equation written as a scattering theory, but that's all it is. And we're getting out the second law of thermodynamics. So what that means is that we're getting thermodynamic quantities from, from static quantities, from just the idea of having equilibrium somewhere in the reservoirs, so having a Fermi-Dirac distribution in the reservoirs. And I would be very interested, this is a new result and I've been looking in the literature, if anything like this exists in classical mechanics, whether there's any sort of derivation of the fact that if you take equilibrium plus Newton's laws, you can get the second law of thermodynamics. I haven't found anything yet, but it's okay. So that's the main thing I wanted to say. Oh, the other thing is that there's a. Okay, so now the quantum bound. So coming back to this quantum bound, you see. This is very new stuff, and I'm not completely sure this is correct, but it looks like the quantum bound, if you have 2 reservoirs, is more strict than if you allow to have many, many reservoirs coupled to your quantum system. So it seems that there's a lower limit on how much heat you can extract from one reservoir if it's only coupled to one other reservoir than if it's coupled to many. Okay, so that I think I will stop there. And just mention that if you compare the quantum bounds to traditional thermodynamics, you see that if you have a nanostructure, the quantum bound is much, much more important than the traditional thermodynamic bound on how much heat you can extract to cool down a system. Okay, so in this silly example that I won't go into the details, it's about 1/10. The quantum bound is about 1/10 the classical thermodynamic bound. But what intrigues me is the fact that if you take a typical kitchen freezer, so you're supplying typically around about 100 watts of power, and you want to cool down from around room temperature to about say, -5 degrees or something like that. then Carnot tells you that you can't, when you're in that situation, you can't extract heat at faster than 13 watts. So you can extract 13 joules per second, okay, from this cold thing that you want to keep cold because heat is flowing in every time you open the door or whatever. What the quantum bound tells you is that you can't extract heat faster than 3.6 watts per square centimeter of your refrigerating element. Okay? So if your refrigerating element was only 1 square centimeter on your refrigerator, actually the quantum bound would apparently be more important than the classical thermodynamics. As soon as it becomes a few square centimeters, already the classical thermodynamics is the most important one. So I don't know what it would be in a typical refrigerator. I guess it's some 30 square centimeters or something like that. So then it's still classical thermodynamics which dominates. But it's not far from the limit. Now, of course, and with this I will finish, of course what I'm saying here applies for a thermoelectric effect, not the real pump system that you have in your kitchen, where I have no idea how to calculate what the quantum limit would be. And secondly, this is always with DC thermoelectric effects. So I'm applying a constant bias and pushing heat at a constant rate. And I think it would be very interesting to look at what happens if you have some sort of pumping cycle, so that you're driving the system periodically. Is there some equivalent bound if you're driving a system periodically? It would be very interesting to think about that sort of problem. Okay, so that's the summary. So I started off trying to convince you that thermoelectric effects could be good for engineers. Then I said that nonlinear physics, non-equilibrium physics in these systems seems to be very rich, and I've got one example where I can more or less solve the problem and see this sort of catastrophe physics. And then it seems that thermodynamics works for these quantum systems, but there are other bounds coming purely from quantum mechanics, from the finiteness of the wavelength, which may be as important or more important, depending on the system, than the traditional thermodynamics. Okay, so thank you.
Okay, thank you for this inspiring talk. So, our tradition is that the first 2 questions are reserved for students.
Okay.
So, who wants to first to be the first one? Anyone? Okay, let's move on to the senior.
I am surprised by this quantum bound on the microscopic refrigerator. This one was not derived under the assumption of some coherence cutting, something like this. I mean, you're missing any dissipation, I guess.
Yes. So the version. Okay. So I think I can include some dissipative effects in the derivation, and it's robust. It's still the same bound. Now it's always an upper bound on the heat you could extract. It's quite possible that a given system would never reach that bound, and maybe dissipation would make any given system better or worse. But it seems like the bound is given by nature. And I think So what I can prove is for particular simplified models of dissipation. What I believe is that it's a very simple thing where if you have a constriction of a finite size, electrons arrive there at a finite rate. So you have a big reservoir which is full of electrons above the Fermi surface and holes below the Fermi surface because it's at some temperature. If the temperature is very low, they're very rare, and so they arrive very rarely at your constriction that you're trying to suck the heat through. You can't do better than every time an excitation arrives there, you capture it. Okay? And so that gives a very fundamental bound on how much heat you can extract. You basically capture every excitation that arrives at this surface.
Any upon the refrigeration by the Peltier effect, by the thermoelectric, but not by the usual refrigerator, the expansion of a gas.
That's a good question. If you think of your reservoir as your turkey inside your freezer that you want to keep cold, then I guess heat excitations in the middle of the turkey still take some finite rates to get out and be, and you can't extract heat faster than it gets to the surface. Maybe it's a similar, maybe that's a sort of classical analog. I'm not sure if it's the same or if it's just similar, but it's the, yeah.
But in this quantum bound, I'm surprised that it does not play any role the temperature of the bath. I mean, you just have one temperature there.
Yeah.
Now, if the bath from where you extract the heat has a huge temperature, there will be a lot of electrons above the Fermi level, and they might go backwards to there. So somewhere there should be a limitation on the temperature of the bath.
Yeah, yeah. I'm thinking about now for the case of a two-reservoir system. But it seems that if you're trying to cool down one reservoir and you're allowed to couple to an arbitrary number of reservoirs, you can bias them in such a way that, I mean, it's...
then you have to have a huge bias, because...
Absolutely not, but this is...
If the reservoir says has a temperature, there's a lot of electrons over there.
Yeah, so you bias, so if there's a lot of electrons, if it's at a high temperature, you have to bias it to make sure that there are no electrons. And this is what I'm claiming, is that even if you do an arbitrary amount of work, which means applying arbitrary big biases of passing arbitrarily big currents, there's still an absolute limit on how much heat you can extract, okay? And that's different from the normal thermodynamic limit, where the thermodynamic limit says that, I guess I had the formula here. Yeah, so if you manage to achieve Carnot efficiency, which is the upper bound on how much this is the heat, the minus sign is just a convention that I chose, which is stupid. So this is a positive number, and it has to be, that's the heat you extract has to be less than this ratio multiplied by the power you supply. So for any finite temperature for your cold bath, you can always supply a lot of heat and extract a lot of power to extract heat at whatever rate you like. In the quantum bound, the power you supply doesn't appear at all. So it doesn't matter how much power you supply, you're always going to be, you're always limited by this.
But it could be worse if you do not bias enough.
Absolutely. There's plenty of ways to be a long way. There's plenty of ways to do things badly. What this claims is that if you do things well, that's the best you can do. Yeah.
And in the first part, you mentioned a cusp somewhere when you included the temp that you had in there.
Yeah.
Yeah, and is that really cusp, or I mean the black line? So the black line again is the one.
So, yes. So if I take, for example, this brown curve, then the correct physics is the temperature drop, the steady state temperature, the one I will achieve if I wait long enough, drops as a function of the current until it hits this point, and then it increases as a function of the current.
Does the black line continues also?
So in that case, for that case, the black line it should stop there. Sorry.
Should stop there. Okay.
Yeah. So it's just that all of the other curves that are hidden are all hidden under the black line, which is the one when there's no. Sorry, that's not very clear. Yeah.
That's fine.
Okay.
Okay, so there were quite a few questions already, so let us thank Rob again.
Just to make an announcement that today is not the birthday of David. He celebrates his birthday tomorrow, but he doesn't